So, like I was saying, autoruns dovetails nicely with the discussion of the service control manager because the whole point of autoruns is that it's something you run on Windows that'll tell you all the places that are set to either run code automatically when you next start up, or if you click on certain applications, they'll also pull in additional code. So this will tell you places where code gets automatically executed because of the system configuration right now. So, and just a miscellaneous thing, recently there was an article by Mark Rusinovich, the person who's one of the authors on Windows internals book, as well as one of the people from the sysinternals before they got bought by Microsoft, talking about how to detect Stuxnet using some sysinternals tools. And he's looking at things like autoruns. He's looking at things to dump memory locations to see injected DLLs and stuff like that. So you might want to check that out afterwards. I don't think really the sysinternals tools are the right tools for the job. I think that things like Gmer and stuff like that, they make it much less manual, but still it does do a good job of showing how it was trying to hide in plain sight. It wasn't hiding its service control manager entry, right? So it was just using SCM, and it wasn't even hiding that entry in the registry. All right, so let's put autoruns onto the system and check it out. It'll also be a good way to show that, again, Hacker Defender will not show up in autoruns because autoruns is not trying to really get around rootkit hiding techniques necessarily with cross-view detection. All right, so in your VM, now just Google autoruns. And the first link should be it. And then just download it to your desktop. And when it's done, open it and extract all files to desktop/autoruns. Again, when the zip file came up, I just used the extract all files link on the side in order to extract it all to the desktop. All right, and then obviously run it when you get it. So just run the regular auto runs. The SC one. Agree to the EULA. All right. So now you see that it goes through and it enumerates. It's basically checking a bunch of places in the registry. Here's the fun part that I found the other day when I was trying to recreate some of this detection using other tools. If you go to Options and you say Include Empty Locations, and then you rescan. So again, Options, Include Empty Locations, and then rescan. It's going to show you all the registry keys and also a couple of file system locations where it's checking. So a bunch of these are empty right now, so it's not showing you anything. But these are all places where where registry could potentially be changed to automatically load code on next startup or in response to certain programs executing. So I think I counted, and there's something like 134 registry locations where it's checking. So only a few of these are filled in, and there's a few file system ones here somewhere too. So like Task Scheduler. Well, so this happens to be one of my things that I added. Task Scheduler is, there's this folder. So right now, it's saying there's these three things, control job, control2.job, control3.job. Each of these runs a command from system32 ctl.exe, and it has some sort of obfuscated commands. The first one is -i:1. The second one is -hk:1. And then this one's a little suspicious. -a:/Windows system32 drivers foo.exe. Right? So this control job is actually the heap or hook kicking off. So like I said, there's different ways that you can start stuff up. For many of the proof of concept ones, I was just lazy and just automatically loaded the driver. In the case of heap or hook, it's supposed to be controlled from a user space exe. And I renamed that exe to control.exe. Just call it something, generic and system32 looking. Right? So control.exe, the -i:1, that says install your kernel module. So the user space thing loads up. It actually uses Service Control Manager, I believe, which is the interesting part. it loads it up. No, does it? Yeah, I think it does because it uses a random name. So it creates a random name for the service, loads it up, and then it gets into kernel, and immediately when the code is in kernel, it copies itself to dynamically allocated memory. And then this user space thing, it just loads it up, waits a couple of seconds, and then unloads it. And so like I said, it's just some randomly named thing, so you would have no association with it. Well, I'll have to double check that again. But loads it up and then unloads it. And then now it's in kernel space. It's using those SSDT, additional SSDT table in order to send commands from user space to kernel space. So the next time you run it, you run control, you say -HK:1. That's telling it hook the IRP tables. So until you issue this command, it doesn't go in and put all those hooks in the IRP major function tables. But once you issue this command, now it goes in and hooks the IRP function tables so it's ready to start intercepting directory listings so it can actually hide files from the system. All right, and then third command, now it's saying -A, add a file to hide, and here's the specific path. So it takes a path for a file and says to the kernel side, start, I know you're already hooking the directory control IRPs so you can hide files. Here's the path of something that I want you to hide now. And in this case, it's hiding foo.exe, which is our other foo2 rootkit. So the foo2 rootkit executes earlier through some other mechanism. Foo2 runs, hides some stuff, and then later on heap or hook overlaps and like hides foo2. So I could have heap to hook hide itself as well. So I could have it hide control.exe, but then it would just show up really easily in Gmer, right? And when you're doing those scans, you'd see, oh, control.exe, that's hidden. So I wanted this to be sort of persistent using some mechanism, but not hidden so that it's like sticking out like a sore thumb. Now that said, you can still find it through things like this. If you go look at Task Scheduler on all these machines, on the physical machines, and again, this is what I want you to do at the end of the day, run auto runs, run Gmer, run virus blockade, things like that on these physical machines, and see if there's any stuff that strikes you as weird on these things. So, all right, so I said key to hook comes in and hides foo2. Foo2 runs earlier. Turns out that is run through, I'm going to get rid of these entries again, so I don't want to do with all those. Turns out foo2 runs earlier due to this bat file that I've created a run key for. So this is kind of a well-known persistence mechanism as well as kicking things off at start. This is a run key where anything that's put into this key is some program which is going to be automatically executed at system start. So the program I set to execute was a bat file, but more specifically, it was a bat file which calls, well, so it's not even a bat file. It's actually, I'm calling wscript, which is the Windows scripting engine. I'm saying run this VBS file. This is a Visual Basic file. And that VBS file then runs whatever is given as the next command. And what it runs is fat.bat. But this VBS file, it just happens to be that VBS is a nice format where you can run this next bat file without it popping up. So it's kind of suspicious when you reboot the system and like there's, unfortunately we deal with it here anyways due to legitimate things that might have run. But it's kind of weird when you see a command window pop up and then disappear immediately at boot, right? But using VBS scripts, you can actually completely hide that pop-up so that the VBS runs and it hides that window so that there's no pop-up, but it did still run. So if we went and investigated this C:\Windows fat.bat, I'm just going to run Notepad here quick. And open up C:\Windows fat.bat. Right, so I just gave it sort of a quasi-legitimate sounding thing. Maybe you think it has something to do with fat file system. I certainly named it fat file system initialization in the run key. But when we actually look at the contents of that bat file, it turns out it's changing directory to C:\Windows System32 drivers where foo.exe is stored. And then foo.exe calls -ph for process hide. And it gives it a PID, process ID. So it's hiding process 4, which is actually, it's kind of inconsistent. Sometimes system is called process 4. Sometimes system is called process 0. But this is the command actually which led to that misclassified shadow walker hiding thing I had to correct at the beginning of today. This hiding process 4 is why Gmer said there's process, brackets 0, because that system is 0, 4 is system. So it's saying there's a hidden process 0, but it didn't know what the name was because system doesn't necessarily have a name, doesn't necessarily have a string associated with it the same way that like notepad.exe does in its data structure. So anyways, I just ran foo to hide a process, and then I installed using this install driver. It's basically just calling out to Service Control Manager, and it's saying create a service called MMPC, and then load MMPC.sys. And this MMPC is actually Shadow Walker. So this is the thing which is going to go in. It's targeting, right now Shadow Walker is hard-coded to look for foo's msdirectx.sys, which is the thing which foo.exe, this user space process. It loads the kernel driver, it just pops it up into memory. Then Shadow Walker comes along, it is looking for msdirectx, it's hiding its virtual memory, it's redirecting its virtual memory access out to different physical memory. So if you went and tried to scan the msdirectx virtual memory, you would just see garbage. And so this is the installation of Shadow Walker. But then finally, yeah, okay, now it finally makes sense. I was like wondering why these two things are hidden when, according to my batch file, like in the wiki, they weren't both hidden. Yeah, so finally, foo then hides its own driver, msdirectx, and then it hides mmpc.sys in order to hide Shadow Walker's driver as well as hide msdirectx. All right, so anyways, that was just the two sort of everything else is pretty much Service Control Manager. That's the only couple places I got a little clever. Expect me to get a little more clever than that with the next VM, the tactical hiding one. It's not going to be this easy next time. But anyways, point is, you can still find a lot of useful information in Service Control Manager. Here we see the Vanquish service. So it's not actually hiding its thing right now because I said it sort of is broken. It's not hiding the file system one either. But it creates a service, and then it would hide this normally if it was running correctly. And then down here, it's saying HKey, local machine, system, current control set services. This is where we looked before, manually in regedit. And here's a bunch of stuff right now, which it considers important to show. There are options up here where you can like hide Microsoft Windows entries. That's useful. And also, you go options and verify code signatures. That's also useful, so that then it'll go through, and for everything that's being auto-started, it'll check, is this digitally signed? So for some of these, like the sys-e, that was our system enter control hook, our system enter hook, where it hooks that MSR. What else is in here? Well, there's Gmer. All right, so there's control to cap. This is the legitimate Microsoft or sysinternals program, right? Now the key difference here, and this is kind of a common thing, sometimes the attackers are not entirely robust about the way they're putting in their registry entries, for instance, right? So back in regedit, right here, this is my msdirectx, this was foo. All we have right now is a display name of msdirectx. I mean, that's better than some. It at least has a display name field. So this says, in Service Control Manager, it's going to show up as msdirectx. Some of the simpler ones, like basic.sys, basic. I guess it does have a display name, so never mind. I thought that some of these were like having empty entries, which is kind of suspicious. Oh yeah, it is. So the display name doesn't count as description. Ah yeah, that's it, description. So when things don't even have a description, sometimes that's kind of suspicious. So all of the, quote, legitimate things are always going to have descriptions associated. Simultaneously, you still have to be aware that attackers can, call their description to make it mislead you and make you think it's a system component. So don't rely entirely on that. This right here, I'm thinking right now, this AZDOWM, I think this is the service that key for hook creates dynamically, just sort of a random name, creates it, and then deletes it. And right now it's saying that it can't even find the file. Or actually, that may be, I may be incorrect, that may be the STPD, whatever thing from daemon tools, associated with daemon tools. Yeah, I think that's what that is. Anyways, lots of good information with auto runs. And so the point I want to make here is there are kind of two ways that you can go about attacking and finding the presence of the rootkits here. For most of the class, we've been focusing, digging deep on the how do you find integrity modifications, how do you find changes to the system, right? Another way you can come at the problem is how do you find how they're persisting on the system, right? How are they staying and running every time that the system starts? Auto runs is extremely useful for digging into that. So just looking at these entries, being able to compare it. Now again, some of these are completely ambiguous and you can't tell, whether that's good, whether it's bad. You don't know whether it's a legitimate component. One way to get around that is to try to start comparing across many systems, which you believe at least some of them are in uninfected versus infected state. Other way is to, do those things like verifying digital signatures. But when you come at it from a persistence side of things, you just need to be aware that something like auto runs is not an anti-rootkit tool. It's not looking for hidden things. But together, they work very well because Gmer will detect hidden services, and this will detect anything that's hiding in plain sight, right? So Gmer is not going to tell you just all of the services. Actually, it does, but Gmer will tell you things that are hidden. This will tell you look in a bunch of more places that Gmer doesn't even look. Those control jobs right here that we had used, and all those other, 137 or however many registry keys that Gmer isn't actually checking. Because if he was checking it, you'd be re-implementing auto runs essentially. Now I say that, but the virus block Ada thing actually is kind of re-implementing auto runs built into the VBA if you still have that open. There is, you'll see over here, there's an auto run checkbox, or if you go to Tool, Auto Run, they're actually sort of re-implementing the auto run stuff. But to me, that just again validates the notion that there's two ways that you can come at the problem: looking for integrity changes and looking for persistence mechanisms, right? So we haven't really talked. I mean, each of these is the mechanism by which someone can potentially persist. Sometimes we talked about some of the things like the master boot record, right? So we know the master boot record, if they're sitting there in the MBR, they're persisting. They're going to be called every time the system is loaded. Installation of the BIOS, that's again persisting. Installation of a, now not like the Blue Pill case where Blue Pill just gets called dynamically and it creates a hypervisor, but the attacker could modify your hypervisor on disk, or they can install their new hypervisor on disk and set that to boot, and then just have it quietly pass on control to the OS, stuff like that. Those are other mechanisms that you can use to persist. So between the two of them, looking for integrity checks and looking for persistence, this is a good way to attack the problem.
With auto runs, you supposedly can run it on and off my system, so if you do it, use this. I was unable to get that to work. Have you had any experience with that?
I haven't tried that, but that's an interesting question. Is that what the SC was for? I can't remember.
Yeah, well, the SC is just command line.
Oh, is it? Okay.
It was regular auto runs that you would load up the keys supposedly and load up offline for instance.
Right, and the thing there was you'd have to do, you'd probably want to do the command line one actually. So you could boot off of a system, like BARP, something like that, or what did it, you said it's supposed to boot off of?
WinP.
So WinP, yeah. Right. So you can boot off a system, but you'd want to maybe use the command line version to just dump everything, and then boot from within the system, dump everything, boot from outside of the system, dump everything, and just diff the two things, and see if anything differs, then okay, there's something going on here, right? And that would be a case where it's like that Ghostbuster that I was talking about before, where you could check file system. This would be checking registry primarily, right? It would be diffing the relevant fields of the registry. So yeah, I should probably play with that at some point. All right, so that's auto runs. Now, we're going to move on to analysis of the system from outside of the system. So thus far, we've been entirely doing it within the system, right? So now we're going to come back a little bit more towards that hypothetical scenario that I put in the original email InfoSec list post about, you're sat in front of a system, and what do you do to actually analyze it while having potentially the least forensic impact on it, right? So for all of this stuff, when we're installing programs, we're overwriting hard drive sectors. When we're loading programs into memory, we're fundamentally changing this data structures in memory and things like that, right? So if we want to have the minimal impact, this is basically how I would recommend going about things. Now, this is going to be a do as I say, not as I do for right here, because we can't do this idealized case in our scenario. If you had a physical machine that you're responding to, you could do this, but not so much here. All right, so ideally, you want to capture the volatile memory, that means the RAM. You need to capture the state of RAM on the system when you walk up to it, and you need to capture the state of the hard drive on the system when you walk up to it, right? So hard drive is pretty well understood, right? Generally, forensics people recommend, pull the plug out so that there's nothing. If you legitimately shut down the system, there can be things that have, for instance, these shutdown hooks, where, they get a callback and they delete something from memory or they delete something from disk. So let's say a master boot record infecting thing has, or a BIOS thing would be better. There's a BIOS thing which has some sectors on hard drive which it reconstructs into a DLL, and then it drops it onto the Windows system. At shutdown, it could potentially delete that so that it would still just be recreated fresh each time. But when it's scattered around on these sectors on the hard drive, it's not an easy target for forensic analysis. And therefore, that's why they would want to delete this recreated DLL each time. So anyways, hard drive is pretty well understood. We're going to focus more on the memory side of things. So ideally what you do is if the machine in question has something like a FireWire port or a PCI Express port, which probably is less common in, well, let's just focus on FireWire for now. We said when we were talking about the taxonomy of rootkit type things, or taxonomy of the ring-based taxonomy, right? Ring -1, ring -2, all that sort of thing. I said external hardware that has DMA access, direct memory access, can be like ring 0, can be like ring -1, can be like ring -2, or ring -1.5, I think is what I said. So in the case of FireWire, actually, I was asked about this morning, so I should probably bring up a reference. In the case of FireWire, a FireWire device is allowed to speak out and initiate DMA access. So it's allowed to speak to the North Bridge and say, I would now like to access this region of memory, and please send me that. I'd like to go access that data now. There's a couple, so since around 2004, Max Dornsife had been talking about this. He'd done some demos. I don't think I can show the videos or anything, but he'd done some demos where he showed that by taking an old school, which was not old school at the time, by taking an old school iPod, the original iPods that actually had FireWire plugs on them, so before they moved to this USB plug that we're all now familiar with, they just had regular FireWire ports. And so you take an iPod, you put Linux on it. Right, so FireWire hacking Linux for the iPod. You put Linux onto the iPod, so now you've basically got a little computer, right? You've got CPU running it, you've got a hard drive, and all that sort of thing. And it's a little computer with FireWire port. And so when you plug this little computer with a FireWire port into another device that has a FireWire port, the little iPod can speak out to the system, talk to the North Bridge over the PCI protocols, and say, I would now like to have direct access to memory. And so that's kind of how FireWire does quick copies. People say the fire in FireWire is due to DMA, it's due to direct memory access. And so the North Bridge says, okay, you're speaking the right protocol, feel free. Here's the memory that you're looking for. So from a forensics perspective, anything that has DMA access is great because you go in and you ask for physical address, a physical, frame 0, and, take 4 kilobytes. So you say, frame 0, 4 kilobytes, I'd like to read that to my iPod hard drive. Frame 1, 4 kilobytes, I'd like to read that to my iPod hard drive. 2, 3, 4. So you can literally say all of the physical frames, which are the physical chunks of memory, RAM, take those pieces of RAM, write them out to a file on your iPod hard drive. All right, so for forensics purposes, that's great. We have a memory dump, and we can now use certain tools to analyze it, tools that we see here in a second. From an attacker's perspective, which is, he was coming at it, both from a forensics perspective, but also saying, you can do attacks with this. From the attacker's perspective, they can go search memory for something like, when you lock your screen, there's some program in the back end which is going to check your password, and if it's good, it's going to let you in, and if it's bad, it's going to prevent you from getting in, right? And so what they do is they go and find that memory where the actual code that does the yes-no check is, and they just flip it so that if you put in an invalid password, it's going to let you in, and if you put in a valid password, it's not going to let you in, right? So they can go in with DMA, they can read that memory out, search memory for the pattern, and they say, aha, there's the pattern for that code I want to change. And then they can write over that code to make it so that it's backwards. And then they can write that chunk of memory back to the host system. And now all of a sudden your program running in your OS is modified. So that can be used for attacks, and that can be used for forensic access to the RAM to get a file without putting anything onto the system, changing the state of the memory. Now it might change it a little bit because Windows might see there's a FireWire device connected, and it may do some auto plug-and-play configuration, but we're still talking much less than installing programs. Now that's the best case. The best case is FireWire capture the memory. The next best case is something like plug in a USB drive with a specific program like Win32DD, which is, it goes into memory and it pulls, again, just grabs all the physical frames and writes them back to disk. So in that case, what you'd do is you'd say, here's my USB drive. I'm going to plug it in. I can see it in Windows. I'm going to double-click this, and I'm going to, well, not double-click. I'll run from the command line, and I'll say, capture all of memory and write it back to the same USB drive. So you haven't changed the file system other than the fact that potentially this exe gets cached in a certain location on Windows, which will do a little bit of a change. But you've just done a minimal change to memory in that you've loaded one program, but you've copied all of the memory for every other program off to disk now. That's sort of the alternative way. And if this is the way I'd recommend, if you want to do it on these physical systems, for instance, you'll see in a second here when we talk about the commands, you can run WinDD, capture all the physical memory here out to a file, and then use the analysis tools we're going to talk about next. But turns out we can't use the ideal, that second ideal way within our thing. So what you would do if you were doing this on these physical systems is, you'd either put it on USB drive, or you can, on these ones, you can just do it naturally. You'd call WinDD, you'd say /f, and then you'd give a file name for putting it on the hard drive. Inside of our VM, WinDD is not working. And therefore, we can't even do this from within the VM. So if we were pretending to be like at a physical machine when we were at the VM, we'd like to just issue these commands and dump the memory out. But it turns out we don't really have to go to that level. Instead, we can use tools. So technically, we don't need to do this step, but we're going to do it anyways. We can take something called bin2dump, which is an associated tool with the WinDD, with the Moonsol's toolkit, which is right there. So this is where you can get the files later on if you'd like to play with stuff. Bin2dump says, I'm going to take a file, a binary file, meaning this is just a a map. This is just an array of those physical frames that you read out of memory. So you said physical frame 0, start of the file. Physical frame 1, next piece. Physical frame 2, etc. It's just a linear map of the physical frames for RAM. Bin2dump converts that over into a crash dump file, which WinDebug is capable of reading. So we're actually going to take the bin, in this case, is actually the vmem file for your virtual machine. So that's the vmem file is the virtual memory. It's really the physical memory that it's using. It's the virtual physical memory that the virtual machine is using. It's just a linear array of fake physical frames. And so we're going to take that, we're going to convert that over into a crash dump file so that WinDebug can open it. And this will show you sort of the second way that you can use WinDebug to no longer be debugging a live system, but actually a dead system. And you can apply this to just crash dumps where if you blue screen, you can open them up in WinDebug as long as the crash dump is written out. Or you can do things where you capture memory and then convert it into a crash dump file. So, all right, so you already have Moonsols installed on this on the host OS here. So I had them install it for you on your desktop, on your actual just plain Windows machine in front of you. There's the Rootkits folder, and then inside of it, there's Moonsol's Community Edition. So go in there, and then you can see it has Win32DD for capturing memory on 32-bit systems, Win64DD for capturing it on 64-bit systems. You can see it's got sys files, so it's actually, again, doing that same old pop-up kernel driver into memory. That kernel driver then is going to grab one physical frame at a time and write it out the disk. You've got bin to dump and dump to bin, so you can take a crash dump file and turn it back into a linear array of physical frames, or you can take a linear array and turn it into a crash dump file. I think really it's only actually some header information or something like that that it tacks on. But then also there's the interesting one, hyber to bin file and hyber to dump. So when you do hibernate on your system, right, it writes memory out to disk so that the next time you start up, it just reads that memory back, that reads from disk back into memory so that you start up into a system that's in the exact same memory state, right? So if you hibernated a system and then it would be off, right? It's got no power to it anymore. A forensic analyst could come around and grab the hibernate file and turn it into a memory analysis file, and then he could just do his normal physical forensics that he does, right? But again, you still probably don't want to do that because the attacker could find out that hibernate's going on and they can remove something from memory, for instance. All right, so open up a command window. And you're going to want to do change directory. And I usually just grab this entire folder path because I don't want to paste it in. So I grab that and I drag that into the command window. And you should have something like that. So do cd space, and then out of your address bar, just grab the entire folder and drop it into the command window. All right, so you do dir in command window, you should see bin to dump, for instance. All right, so start by doing bin to dump.exe space, and now it's going to be input file and output file. So for our input file, we want the virtual machine. We're going to use actually the snapshot thing. So if you go up one directory, up to this rootkits class folder again, in there, there's rootkit class VM _ version 1.1. And then we're actually going to use this file rootkits class VM snapshot 5.vmem. So this is actually when you revert to snapshot, it's reverting to this virtual memory state. All right, so I'm going to drag that into my window where I already have bin to dump. Right, so drag and drop that. And then once we've got that path, then just space, and I'm going to just do blah.dump. Blah.dump. When you do that and press return, it's going to kick off. But again, I just want to make sure everyone's got that. Bin to dump.exe space, paste over that path by just dragging and dropping the thing. There you go. All right. So you've now got a blah.dump file in the same directory as bin to dump. So on your system now, you've got essentially what's a crash dump file. It's the equivalent of a crash dump file. So you should have WinDebug actually on your host OS as well. So if you go to All Programs and debugging tools for Windows, I suggest maybe sorting this list. You can right-click anywhere and sort by name to get it alphabetical. Right, and you should have debugging tools for Windows, WinDebug. All right, so once you have that open, go to File, Open Crash Dump, I believe. Yep, File, Open Crash Dump. Now you're going to have to navigate to that Moonsols folder, which is on your desktop. So click on the desktop, then your rootkits class, and then your moonsolves, and then you got blah.dump. So here's the path. Desktop, rootkits, moonsolves, and then blah.dump. Yeah, so once you're in blah.dump, double check that you have the symbol search path. Again, we want to drag this over the gray so that it fills the entire screen. Go to File, Symbol Search Path, and I guess it looks like it's not filled in here, so I'm going to have to put this in. SRV star C:\Windows/symbols. Star HTTP:// MSDL, like Microsoft Download, MSDL.microsoft.com/download singular/symbols plural. All right, good. All right, so now you are in, essentially, you're outside the VM, but you're in a copy of the memory that was inside the VM. So you now can navigate through the memory just like you did before. So, for instance, as a first example here, I will once again bring up a disassembly window. So click on the little 1.0 or hit Alt-7, split your screen. You should have, no, not working? Let me get the symbol slow. Let me check your passport. No, it's loading. Yeah, no, that's all you see. You just should see loading unloaded modules list, ... It should be fine after that. Right, so let's do the exact same thing we did within the VM before. Let's do bang IDT, !IDT space E. Right, this gives us the address of the interrupt 14 handler, E handler. We're just going to copy that and paste that into the disassembly window. And you should see whether you saw, the Shadow Walker thing or you saw the Toluca thing, you should see whatever you saw before. So we're now outside the system. The attacker can't manipulate our view of everything. We've just got a dump of memory. Whatever we see is what we see. So I'll move the window up a little bit so I can see the bottom. Can you type .reload? No space. Okay, now you're in a good state. So do bang IDT space E. Copy and paste that into the disassembly window. Yeah. So yeah, if you want, you can go into your VM at this point as well. So this is like just a static copy of memory outside the VM for your perusal, and you can go into your VM and see the same thing. And like I said, we can do more advanced commands that I'll show at the very end, and then you can play with these commands at the end of the day to show SSDT hooks and other things. But that's all I want to show for now, because as we know, WinDebug is powerful if you know what you're looking for, and it's fairly manual. It's not a rootkit detector, it's a debugger. And so instead, we're going to use a different tool, Volatility, which is meant to do memory analysis for forensic purposes. But the nice thing is that there was recently a book released, Malware Analyst's Cookbook and DVD. And that has a volatility plugin which starts taking and analyzing some of the memory, looking for the types of things we care about for rootkit detection, and also just other malware detection. So we only needed to do the bin to dump in order to transfer the format so WinDebug could understand it. Volatility can already naturally just read and parse these vmem files out of the thing, or memory snapshot pulled by WinDD. So now let's, from your command window, go cd/volatility 1.4. actually going to make my window a little bit bigger. All right. So you should be in the C:\volatility 1.4 directory. And from here, we can do, well, hold on a second. Before I go into this, let me go back to slides quick, see if I had anything else to say. All right, yeah, so here's just some links. If you're interested in knowing more about volatility, Drew Hunt has a class on memory analysis. It goes over explicitly just volatility. And so this full installation path, this is where you can get a nice walkthrough if you want to install volatility on your own system. And then here's the path of the malware.py file where you Python plugin for volatility in order to run various malware detecting commands. So I also have examples in here of running each of these commands. So let's try this one first to start with. Now, unfortunately, this blah.dump is going to be somewhere else. I maybe recommend going out to Explore and copy that blah.dump file to like C:, just C:, or something like that. That'll make your paths a lot easier. Actually, before we do anything else, let's go to desktop, moonsolves, right? And let's grab that blah.dump and put it over in C:/. So I just dragged and dropped my blah.dump out of moonsolves desktop rootkits, moonsolves. Grab your blah.dump, drag it to C:/. All right, so now back at your command line window, you could, for instance, do this command. We're going to look at for SSTT hook detection. So this is actually the built-in one. This is not the, is this the built-in one? This is the built-in one, but I'm not sure that's the one I actually want to do. Yeah, let's do the built-in one to start with. So from command window, do Python space vol.py space. And if you did, I guess I want to make sure everyone has this installed right now. So just do Python space vol-py space -h for help. And what I want to make sure is that everyone in your commands, you should see, for instance, commands like svc scan, where it says malware, and SSDTX, where it says malware. If you don't see that, the plugin isn't working right now. So is there anyone who doesn't see the malware commands on the end? You got it. You got it. Okay, so let me fix this typo on my slides quick. The vol.py. Wherever you see in my slides vol.sys, change that to vol.py. Force a habit. So first we're going to do Python vol.py space SSDT and then -f, and this would be C:/blah.dump, or whatever your path is to your file. In my case, it's Python vol.py SSDT -f and C:/blah.dump. Alright, I'm going to let that run here for a second. It'll take quite a while. I'll wait to check everything. So basically what volatility does, though, is it has certain signatures for data structures. So what you're giving volatility is just a big blob of all of memory, right? It doesn't know what memory goes to which process or anything like that. And so what it has is a bunch of data structures where it finds things like page tables that we learned about. It finds things like IDT, GDT, stuff like that. And so it just searches using special using special signatures within this thing, and it finds those, and once it finds a particular data structure, then it can start seeing, okay, there's a pointer in this data structure to some other data structure, and this looks like it was pointing at virtual memory, whatever, but then it has to like go find the physical to virtual translation and start mapping, okay, well, if that was pointing at virtual memory this, but virtual memory this was physical memory that, then I can go to physical memory that and start find another data structure. And so it just builds up an increasingly rich set of data structures and knowledge that it can infer about. All right, so what you should see when you run this is something like this. You'll see a bunch of stuff saying win32k.sys owns all the things in the shadow SSD key. I know it's the shadow SSD key because it's saying entry 1 something something something, right? A bunch of those are win32k.sys, and it's not really trying to pass judgment on whether something is hooked or not. It's kind of leaving that up to you. Oh man, I don't have a big enough scrollback buffer. You're probably going to want to change your scrollback buffer in your command.exe to be bigger so that we can hold everything. So right-click on the top left corner, go to Properties. And I think I'll make my text a little bit bigger here in a second. I usually go with the scrollback buffer of 3000. And I'm going to make my screen a bit bigger. That's easy. I have to do this one more time, otherwise I won't find the hooks. So for instance, one thing worth noting is that Gmer doesn't look at the shadow SSDT. So Gmer doesn't tell you if there's any hooks in the shadow SSDT. Whereas this thing is listing all of the regular SSDT and all of the shadow SSDT. And then it's also listing any other miscellaneous SSDTs that it finds. And so this one in particular, this very last 5 entries, this is that key for hook thing that I've been making reference to. And none of our other tools have told us about this yet, because they're not looking for if there's an extra thing in one of those 4 entry structures. But you can see that each of them is pointing at a specific location, and it says owned by unknown because they don't know which kernel module that pertains to, because it's just dynamically allocated memory. It isn't any kernel module. They copied themselves into dynamically allocated memory. All right, so I'm going to see here. I'm pretty sure there is at least a couple of hooks, I think, by trusteer rapport in the shadow SSDT. So I kind of have to manually look through this here quick. Oh, there was one. There's a owned by VS Data NT, so that was Zone Alarm. So Zone Alarm's hooking the shadow SSDT. There we go. There's one. Rapport PG is hooking the shadow SSDT. Zone Alarm again. So I think I didn't run these again. I probably should. Well, it'll be too late by then. So let's go on to the next one quick. So that was just, that'll dump, everything that is in the various SSD keys, but it's up to you in order to sift that out. Now, the plugin ones are a little better here. So that was the default. That's with every volatility. And now this is going to be one which is actually a plugin from the malware one. So we're going to do Python vol.py SSDT underscore by underscore thread, and then -f in your file. And this was looking for those things, the black energy type attacks I was talking about, where for a specific thread, they pull it out and they point it at a different SSD key than normal. And hopefully this is going to work. This used to crash on this memory dump, but I think he fixed that, the author of the plugin. So let's try that. You get an error. All the people think.
It's by threads, but threads.
Let me see quick. It is threads plural. Yeah. SSDT underscore by underscore threads. And yeah, that's another typo. Threads. Now this time it's going to at least try to say if it points at, if the normal SSDT points at NTOS kernel or NT-kernel PA, don't report it. If the shadow SSDT points at win32k.sys, don't report it. So just report everything else that's pointing somewhere besides that. And then finally, at the very end here, it's saying, okay, here is the specific one of those four, that array of four structures. Here's the specific place where this thread is pointing, where that thread is pointing, etc. And so what I was saying before is you should only ever have two of these entries, and they should either point at the shadow SSDT or the regular one. And these look like they all basically point at the same location. It's saying they're bad, but I can't remember. There was some heuristic he was using that I don't recall at the moment. Why that's not necessarily bad. All right, so one thing, again, we see these 5 entries at the end here where it doesn't know what they have anything to do with. And then for the other ones now, it's much more clear. All right, for everything that starts in a 1 right here, entry 1007, that's shadow SSDT that's hooked. So just those entries are shadow SSDT that are hooked. And for all the things that start with 0, those are all regular SSDT. Again, having all of these third-party software makes it much harder to find the actual single rootkit thing that I have in here, right? So the only thing that's actually something I put in the VM that's maliciously doing a hook is this control2cap, where it's control12cap.sys. That's hooking NT-query directory file where that was trying to hide files. That's the thing that hid _cool_beans. But all the rest of this is just third-party software, cluttering up the place, making it difficult to tell what is actually hooking my system at the time. All right, let's do just a couple more here. Well, we got time. Do the rest quick. So SS2T by threads, that's nice. API hook, this is going to be looking for inline hooks as well as IAT hooks. So let's check that out. Python vol.py API hook. API hooks. Looks like API hooks plural to me. No, I think you just need to change to API hooks plural. Right, so now it's going into all the processes that it can find information about. It's going to the physical memory for all of the things. And it's saying, now key differentiator here is that this is just memory analysis, right? Now, actually, I'm not even sure whether they do this would be smart if they did this, but they don't have files that they can compare against right now. When you do something like WinDebug's check image command, the bang check image, it's saying, what does the thing look like in file versus what does it look like in memory? And so here they don't have that. So at least in some things like the, in some cases like the IAT, well, you can deal with that because you can say, well, this should have pointed over there, but it doesn't. For the inline hooks, actually, now I'm curious how they do that. They may be just looking, they may just have a heuristic where they're saying if there's a jump instruction immediately at the beginning, report that. They may have something where they, well, I don't know. I'm going to just hypothesize that that's actually what they're doing here. Because I was going to say maybe if they could find a clean copy, they could compare the clean ones versus the dirty ones. But theoretically, if something like Hacker Defender is going in, it should be hooking all copies in everyone's memory space. So I have to look up what exactly it's doing there. Anyways, you can see that it's got a bunch of inline hooks, and let's see if there are any IAT hooks yet. Well, didn't print any IAT hooks yet, but it would eventually. All right, so that's inline hook. Again, we can get some of the capability back of our other things like Gmer. And then let's go with IRP hooks as, oh, there's one more. All right, so driver IRP. So vol.py, driver IRP. And this may be one of the ones that takes forever. So there's the callback one. I know that one definitely took forever on my systems, and I think I tried it in McLean as well, and that takes forever. Okay, there we go. Not so bad. All right, so this is saying, for instance, let's start at the beginning. Stuff. Lots of stuff. Canceling that. All right, starting at the beginning, it's saying actually MS DirectX, which is the Futu driver. It's saying its create function points at F3C74 blah blah blah, and it's saying it doesn't know who owns that, which kind of makes sense, right? Because we know that this thing is hidden. This msdirectx.sys, it hid itself, it removed itself from the list. So if it's just consulting the list of loaded loaded modules, then it's not going to be able to find it. Then there's this other fields over here, the hook adder and the hook owner, where it's trying to say whether or not this thing is actually being hooked. So I think right now it's just enumerating stuff. It's saying here are the addresses where things are pointing, and then it'll make a heuristic decision of whether that's a hook address, and if so, where it's pointing at. So if we scroll down, we should be able to find something. What? No one's hooked? Interesting. Oh, there was one. Ah, it's reporting its hook as itself. That doesn't seem right. Also doesn't seem right. Alright, so I'll have to investigate what heuristics it's using for that, but you can see that it's not actually reporting any hooks on anything, which should be wrong because we know that he for hook is in there, like changing the changing things like NTFS, it's pointing it over to he for hook instead of internally. Maybe I just didn't let it run long enough, but I'm pretty sure some of those should come up as hook. Alright, last one, we'll just do the IDT one quick. You can do the callbacks one, maybe get it started over lunch because, like I said, it takes a while. So, just IDT, nice and simple. All.py IDT. And in that way, you can see printout of the interrupt descriptor table. All right. So unfortunately, there's much to be desired with the IDT checks right now. But I'm talking with the author about how this can be improved. So for instance, all right, here's the one thing, IDT entry E. Now it's saying it points at KI trap E, which is the name of what it should be pointing at. So KI trap E is the function name for the default legitimate NTOS kernel function. But actually right now this thing is being pointed at Shadow Walker, right? So there's the Shadow Walker address, and it's saying, okay, I can't figure out where that's pointing. Whereas the other ones, it says, okay, I know that's pointing at NT kernel .text section. Now, it's trying to look for inline hooks in the sense that it's saying, if I go to the target of that address, is there a jump instruction immediately at that address? If so, maybe it's an inline hook, right? The problem is, I know that not all of these are hooked, and it's just the default function that Windows fills in for all of these interrupts. The default function just jumps immediately to some common function. So they're all just jumping to the same, like, you shouldn't have called this interrupt handler, right? It's saying, why did you call this? It jumps somewhere and then it errors out. So that's unfortunately a misleading, making it look like everything's hooked when it's not. And then the other problem is, it doesn't have the notion of k-interrupts. So there's a data structure that Windows uses, which thankfully, since we're running nice ahead of schedule, I can talk about this later when I'm talking about kernel object hooking. There's a data structure Windows uses to layer on top of interrupts so that instead of only one function being able to call by interrupt, it can call many possible functions. So sort of like the callback thing, you can register and say, I would like to hear about this interrupt. And then when that kicks off, the OS will come along and call everyone who registered to hear about that interrupt. And so unfortunately, this doesn't, right now Volatility doesn't know about k-interrupt structures, and so it doesn't know how to print out that this is legitimate. If you look at it in WinDebug instead, let's go in WinDebug again and go to Bang IDT 62. Go back on your host OS, do .reload to make sure you've got your symbols. Do Bang IDT 62. And so WinDebug knows what a k-interrupt is. And so it's saying, all right, the literal address of this thing transfers to 825 blah, blah, blah. Actually, that may be right. Yeah. So the literal address transfers to, that's not right. Oh, that's right. Okay. It's saying the literal code where this interrupt occurs is at this first address, 825AC0, blah, blah, blah. So if I wanted, I could go put that into my disassembly window, and I would see some code there. So push EVSP, push EVP, etc. This is actually template code that's always used for these k-interrupt type interrupts. And I'll get into it later. But the key point is there's this k-interrupt data structure which has data at the beginning, and then it has a blob of code at the end. And right now, this IDT entry is pointing at the blob of code at the end of this structure. And it's perfectly legitimate, but the issue is it's in dynamically allocated memory. So the kernel dynamically allocates space for a k-interrupt structure with data and then code. And so the issue is Volatility doesn't know about this data structure, and therefore it just says, this is pointing somewhere other than NT. I don't know where it's pointing because it's dynamically allocated memory. And so it sort of looks suspicious when it need not be. All right. So you can look at the GDT as well. It'll just dump the GDT, and you can find things like call gates, which should never exist there. But go ahead and get the callback started up before we leave for lunch. So Python vol.sys callbacks plural. And then when you come back, hopefully you'll have that. All right, so then you can let that run, and it'll go and do just like virus block Ada did. They're going to go find the data structures, parse the arrays of function pointers for who's going to be called, and then they'll report this out and try to interpret which is actually being called. All right, so any questions right now? Anyone on the phone have any questions? All right, then let's take lunch and be back at 1.